Chip fabricator TSMC recently announced that they were taking orders for their 2 nanometer process, which offers a 15% higher transistor density than its 3 nanometer process, which translates into more transistors per square millimeter. It's thought that Apple will snap up a lot of these for their forthcoming A20 chip, which should be in the iPhone 18, it's believed. And I think Samsung is going to grab some as well. These chips are fabricated on wafers, which have a varying yield depending on what kind of chips are on them. For example, a smartphone SoC would yield maybe 450 or 650 chips on a single wafer, and a larger die like a GPU or AI accelerator might yield 80 or 150 chips on a single wafer. Now, it should be pointed out that the 2 nanometer, well, first of all, a nanometer is a billionth of a meter, so it's really small. For my fellow Americans, a meter is a little bit more than a yard. It's about 4 inches more than a yard. So we're talking something really, really small. But I should point out that when chip manufacturers like TSMC refer to a 5 nanometer or 4 nanometer process, they're not really measuring a specific physical feature of the chip. Instead, these terms are primarily marketing labels that represent a new generation of semiconductor technology with improvements in transistor density, performance, and power efficiency compared to previous nodes. For example, as I mentioned, the 2 nanometer is about 15% more dense than the previous 3 nanometer design. This kind of goes back to Moore's Law, where Gordon Moore, who was one of the co-founders of Intel, made an observation that eventually became known as Moore's Law. It's not really a law, but it's an observation. He states that the number of transistors on a microchip doubles about every 2 years with a minimal cost increase. And that has held for a long time. He made that observation back in 1965, and it's actually held pretty true since then. So historically, process node names correspond to the transistor gate length, or the smallest feature size on the chip. However, since like the mid-90s, this relationship has become less accurate. For example, the gate length in a 5 nanometer process may actually be closer to 18 nanometers. And other features like metal pitch or gate pitch are much larger than 5 nanometers. But the idea is that the new size represents an increase in density, and it's just a convenient label to put on things. Intel has started using an A designation, so it would be 12A, which I think they're referring to angstroms, which is 0.1 of a nanometer. So we're getting down to the size of atoms here when we're talking about this stuff. An atom is 0.1 or 0.5, depending on the size of the atom, obviously. 0.1 to 0.5 nanometers in diameter. I know you can't really measure the diameter of an atom because of quantum stuff, but just bear with me here. In fact, regardless that, 2 nanometers is not actually 2 nanometers, we're still down in the area where quantum effects are starting to creep into things like, tunneling and that kind of stuff, where signals will bleed over gates and stuff. It gets really kind of hairy down at these tiny, tiny sizes. But regardless, the 2 nanometer node is starting to enter production now, and we're going to see more, faster, more dense, less power hungry chips going forward. So we're still kind of on track for Moore's Law. So exciting stuff. So that's another video in the can. If you found this informative or interesting, please consider liking and subscribing down below. And remember, be excellent to each other.